At the time I'm releasing this video, it's winter and cold, but how low can the thermometer go? I don't mean specifically in this part of the world or even in terms of Earth's climate, but in absolute terms, is there a minimum value that can't be surpassed in the universe when we head toward the infinitely cold? And above all, what happens to matter when it's cooled to that level? Get your hats and gloves ready. Today, we're going to dive as cold as it's possible to go, going down the temperature scale, trying to get as close as we can. What we call absolute zero, a temperature whose value in degrees Celsius is exactly minus 273.15 degrees. Or 0 Kelvin if we use the temperature scale that sets zero at that level. The fact that the temperature difference separating us from absolute zero is only about 300 degrees might seem quite surprising. I mean, when you think about it. The temperature of this room is 3 times farther from that of a lighter flame, which is around 900 degrees, than it is from absolute zero. And yet, you'll see that this closeness is just an illusion. And as we descend, as we get closer to this strange limit, things are going to become extremely bizarre. Get ready to see air liquefy, then solidify, superfluids climbing up walls, currents flowing endlessly, matter merging into one wave with even light eventually stopping. Because where we're about to venture, matter won't just freeze, it will behave in completely crazy ways, literally changing identity by inventing new states. To explore the coldest depths, we'll begin by lowering the thermometer from 0 degrees Celsius. This temperature, when fresh water at atmospheric pressure freezes into a solid, might seem ordinary to you. It marks the boundary between two worlds. One is liquid, where water molecules move around, slide over each other, and reorganize together like a moving crowd. And the other is where the dance of water molecules has stopped, to become fixed in the geometric form of a crystal that we call ice. Something strange is already happening, because unlike almost all other liquids that contract when they solidify, water expands. Ice is less dense than water, because at the atomic scale, the hexagonal crystal structure that forms when water freezes takes up more space than the disorganized water molecules in the liquid. This allows ice to float, and this little detail has absolutely fascinating consequences. If ice were denser than its liquid form, then it would sink. And in winter, when the surface of lakes, seas, or oceans freezes, the ice wouldn't form a cover protecting the water below from cooling, but would settle at the bottom, where it would keep accumulating, until it would eventually freeze entire bodies of water in the coldest latitudes. Fortunately, for living beings evolving in the ocean, that's not the case. And when, at exactly minus 1.8 degrees C, the first ice crystals form on the surface of the Arctic and Antarctic oceans, they don't sink, but instead clump together to form the first layer of sea ice. Second peculiarity. As the temperatures keep dropping, the shapes of snowflakes become more diverse, and a new variety of ice crystals appears every 2 to 4 degrees, starting at minus 20 degrees. The sound of snow changes when you walk on it. It starts to crunch. This new sound occurs because the air is now so cold and dry that snow crystals no longer melt when they touch. And at these temperatures already, even though the outside world still seems familiar, something has irreversibly changed. Everywhere, living things quietly retreat and adapt. In plants, the sap slows down. In animals, the blood thickens, and many species, in order to survive, burrow underground or go dormant. They slow their metabolism or alter cell composition, since at minus 20 degrees C, cell water may freeze, by forming ice crystals inside them, which take up more space and can make them burst by destroying the cell walls. At those temperatures for furless mammals like us, The biting cold then stimulates sensors in the skin that alert the brain, causing the sensation of a burn without a flame. When temperatures fall below -25°C and microscopic matter keeps contracting, the surprising Mpemba effect occurs. Oddly, this means hot water freezes faster than cold water. This lets you do cool things by tossing boiling water into the air. From -40°C, it's so cold that if you spit, your saliva freezes before it even hits the ground. And beyond -60°C, the insects that are able to survive the Arctic winter, whose tissues are rich in glycerol and sweet alcohol, which prevent them from freezing, also start to die from the cold. And it's at this point that most steels become brittle. Below -70°C, the polar cyanobacteria that are found bubbling in frozen lakes or in the crevices of rocks also enter dormancy. From that point on, even living beings with cryoprotectants and able to survive such conditions aren't really alive anymore. The archaeobacteria and seeds capable of surviving lower temperatures haven't exactly given up the ghost yet. But the life within them is nothing more than an ember waiting for a new breath. And as the temperatures continue to plummet, certain gases begin to do the same. At -78.5°C, carbon dioxide solidifies and turns into ice without passing through its liquid state, forming what is known as dry ice. Its ability to sublimate, to return to a gaseous state as soon as the temperature rises above -78.5°C, is widely used to freeze things quickly or to create fog effects in winter when the temperature at the pole drops for several months. Below the freezing point of carbon dioxide, which makes up 95% of the Martian atmosphere, it condenses and settles on the ground, forming gigantic seasonal polar caps. Caps that, at the peak of the polar winters, are made up of nearly a third of carbon dioxide ice sheets. And when these regions are once again exposed to sunlight and the temperature rises in summer, the carbon monoxide, too, that has settled sublimates and returns to its gaseous state. This phenomenon can also occur naturally in Antarctica, where the planet's lowest surface temperature of -89.2°C was recorded. And if you ask how long a human can survive without equipment at the minimum temperature of the white continent, the answer is chilling. With minimal clothing and no wind, you would lose consciousness in minutes. Go below -100°C. Almost all solid materials around you, whether biological, metallic, or plastic, become easy to break. That's how much the cold weakens their cohesion. And as the thermometer keeps dropping, the gases fall one after another. Xenon liquefies at -153.3°C. Krypton condenses now, and at -161.5°C so does methane. There are actually gigantic lakes of it on Titan, the fascinating moon of Saturn, where the surface temperature is between -180°C and -182.9°C. Oxygen enters the liquid phase, taking on a strange pale blue, almost ghostly color. Highly reactive and magnetic, this strange liquid clings to magnets, as you can see in this video. Argon condenses at -185.8°C, while fluorine does at -188.1°C. And to see the most abundant element in Earth's air, in turn, surrender and fall to the ground. You have to go down to -195.8°C, the temperature at which nitrogen, the main component of air, also turns into a liquid. This is very useful for performing more or less spectacular demonstrations, like dipping flowers into it, whose frozen petals become more brittle than glass. Worldwide, liquid nitrogen baths are used to cool instruments, materials, and for preservation. Because the area below 100°C is the one preferably chosen for cryogenics, to preserve eggs, sperm, embryos, and sometimes even entire bodies, in the hope of a potential awakening in the distant future. At minus 205 degrees Celsius, you're colder than Uranus's average surface temperature. 220 degrees colder than Neptune, 230 degrees colder than Pluto. Meanwhile, many elements that changed from gas to liquid have started to crystallize. Nitrogen solidifies at minus 210 degrees C, just 15 degrees C below its liquid state. At minus 218.8 degrees, oxygen hits its freezing point and crystallizes. Below 240 degrees C, even noble gases eventually yield. Neon becomes liquid at minus 246 degrees C, and hydrogen atoms, which are the lightest in the universe, eventually yield to the relentless cold and accept a liquid form at minus 252.9 degrees C. At this stage, at atmospheric pressure, there is no element that can remain in a gaseous state, except for the one that gives its name, because it was first observed in the Sun, helium, which still refuses to liquefy. This stubborn element will keep dancing as a gas until minus 268.9 degrees C, the temperature at which it finally becomes liquid, and which lies at the edge of a new world. Beyond minus 270, every tenth of a degree makes our brains work harder, by revealing properties of matter that were previously unknown to us. And things as crazy as the illusion of perpetual motion, perfect energy storage, quantum levitation, and even superfluidity appear at minus 271 degrees C, which is just 2.15 degrees above absolute zero. Liquid helium suddenly loses all viscosity and becomes a superfluid in this unique state found nowhere else in the world. If liquid helium is in a ceramic container, it starts to escape by passing through the bottom, flowing between the atoms, right through the material. If the container is made of glass, then the arrangement of the amorphous atoms prevents the helium from passing through, and it will escape by climbing up the sides through capillarity. As shown in these fascinating images, in its superfluid form, liquid helium even has zero viscosity. So if you set it in motion in its container, it will keep spinning forever, never slowing down for eternity. Or more precisely, as long as you manage to keep the experiment below minus 171 degrees Celsius. Because it doesn't matter if your container is made of superglue, glass, or Velcro. At these temperatures, liquid helium has no friction with any material in the known universe, nor with itself. Finally, the ultimate property that might make your brain overheat at these temperatures, liquid helium even conducts heat instantly, as if every atom in the mixture knew exactly how agitated the others were. And as the heat keeps disappearing, the sense of wonder only grows, revealing more and more new behaviors. It's not so much that the laws of nature start to break down, but from this region below minus 170 degrees C, quantum behaviors become dominant, to the point that nothing resembles the world we know anymore. It's at these temperature ranges that we discover things for the first time. We realize that when exposed to an electric field, certain materials start to do something extraordinary. They let electrons pass through without any resistance, thus becoming superconductors. And that's extremely strange, because at everyday temperatures, absolutely all metals, even the most conductive and pure ones, offer some resistance to the flow of current. And that's the reason why all our electrical devices heat up when we use them. This is because the electrons that move at high speed along the wires are always slightly disturbed by the presence of impurities, by tiny defects in the structure of the material, as well as by the vibrations of the atoms themselves. But in these realms of extreme cold, the normally disordered electrons stop being single and start forming pairs. Thus, they move like a unified wave, able to glide through the crystal lattices of metals without encountering any resistance. This strange phenomenon of infinite electrical conduction was first observed in the early 20th century, and for 75 years it was only known in certain metals and metal alloys, always at temperatures below -140 degrees. But since 1986 we have managed to bring out this extraordinary property of matter in certain ceramic oxides, which let current flow without resistance at temperatures as tropical as -135 degrees and even close to -20 degrees, under pressures several million times higher than those of our atmosphere. This may seem abstract and unrelated to your daily life. But it is the discoveries of these crazy properties that have indirectly made it possible to develop extremely powerful electromagnets. Because by being able to eliminate the resistance of metals, we were able to run powerful currents through huge coils cooled with liquid helium, and thus turn closed circuits into temporary magnets. So powerful that they allow us to do crazy things, like looking inside objects using MRIs. The discovery of superconductivity also revealed another amazing behavior associated with it: levitation. A fascinating phenomenon at the border between the classical world and the quantum world, where extraordinarily cooled matter starts to float as if by magic, suspended above magnets. And today, it can be observed at temperatures as high as -181 degrees Celsius using very specific alloys. When a superconducting material is placed in a magnetic field, it generates a perfect electric current on its surface, which creates a sort of anti-magnetic bubble around it. A field opposed to that of the magnets below, which in itself is already strange. But what's even stranger is that this material remains locked in place, while still being able to slide. So it's possible to tilt it, even turn it upside down. Because, at these temperatures, lines of force form between the superconductor and the magnets, gripping it like invisible threads. Even crazier when you get as close as 0.1 Kelvin or less than -173.05 degrees if you prefer. We discovered a state of matter that was previously unknown to us. A state in which the individuality of particles disappears and transforms into a single wave-like cloud, a condensate, one of the most fascinating manifestations of quantum physics in the realm of extreme cold. To make this type of exotic matter appear, you have to isolate particles that are capable of sharing the same energy level, which are called bosons. Then cool them to extremely low temperatures, just a few millionths of a degree Kelvin. At first, these particles move freely, but as the temperature drops, they keep slowing down, and the size of their probability clouds increases. In other words, the more the particles slow down, the more their associated wave functions stretch out. And when these particles reach the lowest possible quantum energy state, and the size of their waves becomes larger than the average distance between two atoms, almost instantly a condensate forms, known as a Bose-Einstein condensate, in which the thousands, sometimes even millions of particles that were there before, merge their wave functions to collectively adopt the same quantum state, the same energy level, and together form a single giant wave function. All the particles that contributed to the formation of the condensate have then lost their individual identity. They have in a way overlapped and synchronized, so that it has become impossible to distinguish them from one another. They then behave only in a coherent and collective manner. I won't dwell on the subject, their wave already does that. These condensates, whose existence was predicted 75 years before we were able to make them for the first time in 1995, are not just strange. They are also incredibly beautiful and extremely fragile. They can only exist when protected from the outside world by a magnetic field and in a high vacuum. Even minimal contact with a warmer environment disrupts their cohesion, turning them back into a simple gas. Maybe even stranger. Okay, it already was. These condensates make it possible to slow down and even stop light. Yes, you heard that right. Stop light. So in itself, slowing down light a bit isn't anything extraordinary. Because while it travels at nearly 300,000 kilometers per second in a vacuum, its speed drops to just 225,000 kilometers per second. In water, it's 197,000, in glass, 124,000, but what about a condensate? By the late 1990s, scientists managed to slow down light to the point where it moved slower than a commercial airplane. Then, soon after, slower than a car. In the 2000s, they nearly stopped it completely. This achievement is one of the avenues currently being explored to develop new ways of storing information on a very small scale, with the goal of developing quantum computers. As for the very strange fermion condensates, they only form at temperatures 2 to 5 times lower than those of Bose-Einstein condensates. And I'll spare you the explanation here so that both you and I can keep our hair. The similarities they share with the interiors of neutron stars and other exotic celestial bodies in the cosmos give us the opportunity for a deeper understanding of the fundamental laws of the universe. And I have to say, I like thinking about the fact that the most tired light in the universe, the one that's cooling down, after 13.8 billion years of space expansion, it reaches us with a temperature of only minus 270.4 degrees, just like the one coming from the Boomerang Nebula, whose measured temperature is minus 272.15. In fact, the coldest place we've found in space, both of them, are much warmer than the coldest place in the universe known, which was created in our laboratories on Earth, where small groups of atoms were cooled using ingenious laser beam systems whose carefully adjusted impacts allow energy to be removed. To the point of reaching record low temperatures, just a few millionths or billionths of a degree above absolute zero. And I think you'll agree with me that that's extremely cold. In fact, this value seems so close to absolute zero that it almost makes you think we're just this close to reaching it. Except that's not the case at all. Even just a few picokelvins from absolute zero, there's still a huge temperature gap separating you from it. To understand why, you have to remember that at the atomic scale, temperature is movement. Cooling matter means slowing it down. So, for fun, it's been calculated that in air at 27 degrees Celsius oxygen molecules move at an average speed of about 1,800 kilometers per hour. Whereas at minus 40 degrees, those same air molecules only move at an average speed of about 1,500 kilometers per hour. Obviously, it's impossible to know the exact speed of each of the roughly 10 billion molecules found in just 1 cubic centimeter of air. They all collide and bump into each other constantly, and some of them certainly have speeds close to zero, while others can move much faster than the average. In fact, it's because these molecules as a group have no preferred direction that they only keep their speed for very short distances, until they run into other molecules. Has anyone ever seen a storm suddenly break out like magic in their living room? The thing to remember here is that the temperature of an object is actually nothing more than a measure of the average agitation of the atoms that make it up. And the greater this excitement is, the faster their movement, and therefore the higher the temperature. In short, the hotter it is, the more agitated it is, and the colder it is, the less movement there is. Absolute zero therefore corresponds to the moment when the atoms, like their components, completely stop vibrating. It's a point where there is no more thermal agitation, no movement, and in doing so, absolute zero is by definition unattainable. At that level, the descent into the cold depths stops. It's perfect stillness, total freeze, since it's not possible to move less than not moving at all. And then there's one last oddity that I've saved for the end. At absolute zero, all forms of light go out, because any object with a temperature emits electromagnetic radiation, mainly in the form of infrared. The hotter an object is, the more it radiates, and the colder it is, the weaker its radiation, and the more it's shifted toward longer wavelengths. But since at absolute zero thermal agitation stops completely, matter should be plunged into perfect darkness. Except that's just in theory, because in reality, at the tiniest scales, the laws of thermodynamics prevent matter from being perfectly still. At this limit, there is always a tiny amount of heat left, an irreducible last breath, a residual quantum vibration called zero-point energy. And it's this zero-point energy that means even at just a few billionths of a degree above absolute zero. And while all the other elements in the known universe have long since frozen, helium still remains in a liquid state. Because the residual motion of these atoms prevents them from bonding, making it the only element in the known universe that can't be solidified unless you put it under pressure. In this sense, absolute zero is a horizon that is as unattainable as it is insurmountable. You can get close to it but never actually reach it because there is always a final ember that refuses to go out. And even if we did manage to reach it, we would surely discover movement arising from nothingness. Because the void between the particles, the space-time on which they rest, never knows rest. When we study vacuum behavior in the lab, we find it sometimes fluctuates, with quantum fields quivering and particles appearing and disappearing. In the universe, total rest does not exist. Even where heat dies, silence is inhabited. It is not the only object with a soundless void. Immerse yourself in the opposite direction to uncover matter's secrets. By climbing the temperature scale up to the infinitely hot, you'll find another video here.